US Physics Olympiad, year 2012, USAPHO, Semifinal exam. This exam consists from 6 problems. First day there are 4 problems, which is part A, and the next day there are 2 problems, which is part B. For each day there are 60 minutes for all problems. Solutions for all problems you can find below this video in the description reference. Problem A1. A newly discovered subatomic particle, the S meson, has a mass m. When at rest, it lives for exactly tau equal 3 by 10 power negative 7 seconds before decaying into 2 identical particles called p mesons that each have a mass of alpha m. Part A. In a reference frame where the S meson is at rest, determine first the kinetic energy, second the momentum, and third the velocity of each p meson particle in terms of m, alpha, the speed of light c, and any numerical constants. Part B. In a reference frame where the S meson travels 9 meters between creation and decay, determine first the velocity and second kinetic energy of the S meson. Write the answer in terms of m, the speed of light c, and any numerical constants. Problem A2. Solution for this problem you can find below this video in the reference of the description. An ideal but not necessarily perfect monatomic gas undergoes the following cycle. The gas starts at pressure P0, volume V0, and temperature T0. The gas is heated at a constant volume to a pressure alpha P0, where alpha greater than 1. The gas is then allowed to expand adiabatically. No heat is transferred to or from the gas to pressure P0. The gas is cooled at a constant pressure back to the original state. The adiabatic constant gamma is defined in terms of the specific heat at a constant pressure Cp and the specific heat at a constant volume Cv by the ratio gamma equal Cp over Cv. Questions. A. Determine the efficiency of this cycle in terms of alpha and the adiabatic constant gamma. As a reminder, efficiency is defined as a ratio of work out divided by heat in. B. A lab worker makes measurements of the temperature and the pressure of the gas during the adiabatic process. The results in terms of T0 and P0 are in this table. Plot an appropriate graph from this data that can be used to determine the adiabatic constant. C. What is gamma for this gas? US Physics Olympiad, year 2012, USAPHO, Semifinal exam. Problem A3. Solution for this problem you can find in the reference of the description below this video. 2 infinitely long concentric hollow cylinders have radii A and 4A. Both cylinders are insulators. The inner cylinder has a uniformly distributed charge per length of plus lambda. The outer cylinder has a uniformly distributed charge per length of negative lambda. An infinitely long dielectric cylinder with a permittivity epsilon equal k epsilon 0, where k is the dielectric constant, has inner radius 2a and outer radius 3a. Is also concentric with the insulating cylinders. The dielectric cylinder is rotating about its axis with an angular velocity omega much less than c over a, where c is the speed of light. Assume that the permeability of the dielectric cylinder and the space between the cylinders is that of free space, μ0. Question A. Determine the electric field for all regions. Question B. Determine the magnetic field for all regions. US Physics Olympiad, year 2012, USAPHO, semifinal exam. Problem A4. Solution for this problem you can find in the reference of the description below this video. Two masses m separated by a distance l are given initial velocity v0 as shown in the diagram. The masses interact only through universal gravitation. Questions. A. Under what conditions will the masses eventually collide? B. Under what conditions will the masses follow circular orbits of diameter L? C. Under what conditions will the masses follow closed orbits? D. What is the minimum distance achieved between the masses along their path? US Physics Olympiad, year 2012, USAPHO, semifinal exam. Problem B1. Solution for this problem you can find below this video in the reference of the description. The particle of mass m moves under a force similar to that of an ideal spring, except that the force repels the particle from the origin. F equal positive m alpha square x. In a simple harmonic motion, the position of the particle as a function of time can be written in form of a cosine omega t plus b sine omega t. Likewise, in the present case we have x as a function of t for some appropriate functions f1 and f2. Question A. f1 and f2 can be chosen to have the form exponent power rt. What are the two appropriate values for r? Question B. Suppose that the particle begins at position x at point 0 equal x0 and with the velocity v at point 0 equal 0. What is x as a function of t? Question C. The second ideal particle begins at position x at 0 equals 0 with the velocity v at 0 equal v0. The second particle becomes closer and closer to the first particle as time goes on. What is v0? US Physics Olympiad, year 2012, USAPHO, semifinal exam. Problem B2. Solution for this problem you can find below this video in the description reference. For this problem, assume the existence of a hypothetical particle known as a magnetic monopole. Such particle would have a magnetic charge Qm, and in analogy to an electrically charged particle would produce a radially directed magnetic field of magnitude B equal mu0 over 4 pi multiplied by qm over r square, and be subject to a force in the absence of electric fields F equal qm multiplied by B. The magnetic monopole of mass m and the magnetic charge qm is constrained to move on a vertical, non-magnetic, insulating, frictionless U-shaped track. At the bottom of the track is a wire loop whose radius b is much smaller than the width of the U of the track. The section of track near the loop can thus be approximated as a long straight line. The wire that makes up the hoop has radius a much smaller than b and the resistivity ρ. The monopole is released from rest a height h above the bottom of the track. Ignore the self-inductance of the loop and assume that the monopole passes through the loop many times before coming to a rest. Question A. Suppose the monopole is a distance x from the center of the loop. What is the magnetic flux Fb through the loop? B. Suppose in addition that the monopole is traveling at a velocity v, what is the EMF E in the loop? Question C. Find the change in the speed dv of the monopole on the trip through the loop. Question D. How many times does the monopole pass through the loop before coming to a rest?